everyone. Good afternoon. We can continue with lectures for MM103. Continue with one example. Can you see my screen now?
Yes, sir.
Okay, we continue with another example. In this example, we want to determine the shear and moment distributions produced in the simple beam by the 4 kilonewton concentrated load. This is similar to the first example. Of course, the first example was solved parametrically, but this one I want to solve this example numerically. So we have one concentrated force, 4 kilonewton, and the beam is simply supported, and we will have two reactions at this pin. Since there is no external force in horizontal direction, so only we will have one reaction in vertical direction, and one reaction we will have at this roller connection. By using the moment equation or force equation in vertical direction, we can obtain these two unknowns. So we can easily write the free body diagram of this structure and obtain the external force, and then we can obtain the sections. So this is the internal the external analysis for this beam. Here we wrote the moment about R1, which is this point. When you write the moment about this point, you can easily calculate the R2, which is the reaction in this point at the right support of the beam. So when you write the moment equation, we will have 4 kilonewton here. The moment due to this force is equal to 4 multiplied by its arm, which is this length, and it's equal to 6. And also we have one moment due to R sub 2, and the moment due to this force is equal to R sub 2 multiplied by its arm, which is this length, and it's equal to 10. So from this simple equation, we can solve and obtain R sub 2, which is 2.4 kilonewton. Also, we can write the force equation in vertical or in y direction. It must be equal to 0. So we will have R sub 1 plus R sub 2 minus 4. It must be equal to 0. So we can obtain R sub 1 from this equation, because R sub 2 is obtained from the first equation here. So we can obtain that R sub 1 is 1.6 kilonewton. So this is the external analysis, and the next step, we need to obtain the internal shear force and bending moment in this beam. For this case, how many sections do we need to obtain all of the shear force and bending moments? Any idea? How many sections do we need to obtain the shear force and bending moment in this beam? Yes, one section here between R1 and 4 kilonewton force, and another section here between 4 kilonewton force and R sub 2. So we can write the free body diagram for the first section. The first section is for x between 0 and 6. This is the interval for the x between 0 and 6. When you plot the free body diagram, we only have the R sub 1, which is 1.6 kilonewton. We have the shear force in the section and the bending moment M. The direction are according to the standard assumption. It means that the shear force is in downward direction and bending moment is counterclockwise. Now we can write the force equation and moment equation for this free body diagram and obtain the unknowns V and M for this part of the beam. So if you write the moment equation about R sub 1 here, about this point, sorry, about this point, because this is not R sub 1, if you are calculating the moment about the cut point, in fact it must be the cut point, it's not R sub 1. So when you write the moment about this point, the shear force V will not appear in the equation because it is located exactly on the cut point. The 1.6 kilonewton force create the moment, and its moment is equal to the force multiplied by its arm, and the arm is equal to x. So it will be m minus 1.6 is equal to 0, and the direction is up to you. Here I assume that the counterclockwise direction is positive, so m will be positive, and the moment due to this 1.6 kilonewton force, because this is in clockwise direction, it will be negative, and here we have one negative sign, as you can see. So this is the first equation, and we can obtain the moment in this interval. So for this x between 0 and 6, m is 1.6 multiplied by x, and the force equation in y direction, it must be again equal to 0 because we have the equilibrium condition. In vertical direction or in y direction, we have 1.6 kilonewton force here in upward direction, and the shear force V, and finally it must be equal to 0. The shear force is in downward direction, so it has a negative sign. So 1.6 minus V is equal to 0, and finally we can conclude that V is equal to 1.6. So if I ask you that what is the value for the shear force and bending moment at x is equal to, for example, 4, you can substitute into this equation. The shear force is constant and it's equal to 1.6, but the bending moment is equal to 1.6 multiplied by x, which in this case x is equal to 4, so it's equal to we should substitute 4, and finally the bending moment is equal to 6.4. Okay, so this is the bending moment at x is equal to 4. Or if I ask you about the bending moment at x is equal to 5, you only need to substitute x is equal to 5 in this equation, and then you can extract that m is, for example, 1.6 multiplied by 5, which is equal to 8. So you can obtain the bending moment at each point in this interval between 0 and 6, and for the shear force in between 0 to 6 is equal to 1.6, and this is a constant value. So this is the first section, and for the next section we need to use another cut between 6 and 10. So the next one, x is located between 6 and 10, and in this interval, again, if you plot the free body diagram, in addition to the R sub 1, which is 1.6 kilonewton, we have another force, which is 4 kilonewton. Now, we can write the force equation and moment equation. Again, if you write the moment equation about the cut point, not R sub 1, we will have a moment due to R sub 1, which is R sub 1 multiplied by X. This length is X, as you know. This is X. This length is equal to 6, and this length is equal to x minus 6. So the moment due to R sub 1 is multiplied by its arm, which is x, so it will be R sub 1, which is 1.6. And also we consider that, for example, the counterclockwise direction is positive, so R sub 1 moment about this point is negative because it's in clockwise direction. We will have one negative sign, as you can see, multiplied by 1.6 multiplied by its arm, which is x. And finally, we have another moment due to this 4 kilonewton force, and this is in counterclockwise direction, and it's equal to 4 times by its arm, which is this length, and it's equal to x minus 6. So it's 4 multiplied by x minus 6, and finally it must be equal to 0. And of course we have this moment m. From this equation you can obtain m. As you can see, this is the m for this interval for x between 6 and 10. And to obtain v, we can write the force equation in y direction. We will have this 1.6 kilonewton. We have 4 kilonewton in downward direction, which is negative, and we have v, which is in downward direction, and again it's negative. So from this equation we can obtain that v is equal to minus 2.4. Again, you can see in this interval the shear force is a constant value, but the bending moment is a function of x, and to obtain the bending moment in this interval you need to substitute the x value. For example, if I ask you that what is the bending moment at x is equal to 9, you need to substitute in this equation x is equal to 9. I mean it's equal to minus 2.4 multiplied by 9 plus 24. This is the bending moment at x is equal to 9. Another point that you should consider, and in fact you can use this point to check your results, to in fact to validate your results. At this point, which x is equal to 6, when you substitute in this equation, you will obtain one value for m. For example, when you substitute m, x is equal to 6, you will obtain that m is equal to, for example, 10. I don't know, I should calculate it. Again, if you substitute in the previous slide for the interval x between 0 and 6, if you substitute in the equation for the bending moment, you substitute x is equal to 6, again you should extract the same value, I mean, for example, 10 for your bending moment. Okay, by this method you can check your results. If you made a mistake in your calculation, here you can find out, because at this point the bending moment must be equal. Okay, so by this method you can check your results, and you can find out if you made any mistakes. Okay, so this is the total procedure and the shear force and bending moment for this interval. Any question? Is it clear? Okay, and if you plot the results, as you can see, this is the shear force versus x. The shear force for x between 0 and 6 is equal to 1.6, as you can see, and for the interval between 6 and 10, the shear force is equal to minus 2.4. So this is the shear force versus x, the diagram for shear force. And for the bending moment, when x is between 0 and 6, this is the line of the bending moment. And if you, for example, substitute x is equal to 5, here you can find its value for the bending moment. And for the interval between 6 and 10, this is the diagram for the bending moment if you plot from the previous equations in the last slide. Okay, so these are the diagrams for bending moment and shear force. Okay, the next example, here we have a beam subjected to a distributed load. Draw the shear and bending moment diagrams for the beam AB. The distributed load of 40 Newton per centimeter extends over 12 centimeter of the beam from A to C, and the 400 Newton load is applied at E. So this beam is subjected to one distributed load here, as you can see, 40 Newton per centimeter. And also we have one 400 Newton force here at E. Again, similar to the previous examples, the first step, we need to obtain the external reactions. So we need to plot the free body diagram for the whole beam and obtain the reactions. And after that, we can obtain the internal shear force and bending moments. So the first step, we can plot the free body diagram for the whole beam. Okay, this is the free body diagram for the whole beam. Again, we have one reaction at point A, which is a roller connection. We have two reactions, Bx and By, at the pin connection B. We have one distributed load, which is 40 Newton per centimeter. The equivalent resultant force for this distributed load is 40 multiplied by 12 centimeter, which is 480 Newton. And the position of, or the act point of this resultant force is exactly at the center of this rectangle, and it's located here with a distance of 6 centimeter from point A. We have one 400 Newton force at point E, and now we can write the force equation and moment equation to obtain A, Bx, and By. Bx is clearly 0 because there is no external force in horizontal direction. To obtain By and A, we can write a moment equation about point A or B, and then we can write the force equation in Y direction. If you write the moment equation about point A, we will have a moment due to this force, 480 Newton multiplied by its arm. We have one moment due to this force, 400 Newton multiplied by its arm, which is 6 plus 16. And finally, we have one moment due to this By multiplied by its arm, which is 6 plus 16 plus 10. So if you substitute and simplify and consider a positive direction for the moment, for example, assume that the counterclockwise direction is positive, the moment due to By about point A, according to this direction, is positive because it's counterclockwise. The moment due to 400 Newton is clockwise, and it will be negative. As you can see here, we have one negative sign. And the moment due to this 480 Newton force is again negative because it's clockwise, and here we have one negative sign. So we can substitute and simplify. Here we have one equation with one unknown, By, and from this equation you can solve it and obtain By. Now you can write a force equation, or here we use a moment equation again about this point B. For this purpose, we can write the moment about B. We will have a moment due to this 400 Newton multiplied by its arm, which is this time it's equal to 10 centimeter. We will have a moment due to this 480 Newton multiplied by its arm. The arm is equal to this length, and it's equal to 10 plus 16. And finally, we have a moment due to this force A multiplied by its arm, which is 6 plus 16 plus 10. And then we can consider a direction for the positive direction of the moment. For example, we can assume again that counterclockwise direction is positive. So the moment due to the 400 Newton is positive. The moment due to this 480 Newton is positive as well. And the moment due to this A, because it's in clockwise direction, will be negative. From this equation with one unknown A, you can solve it and obtain A, which is 550 Newton. So this is the external analysis, and now we can solve and obtain the internal reactions. But first, to simplify this beam, and in fact to decrease the calculations in our solution, it's better to remove this arm. I mean, this arm, which is DE, can be removed, and instead of this arm, we can substitute with a system of force and couple. You know, if you plot this arm, we will have one, the free body diagram for this arm, we will have one 400 Newton force here, and we will have one reaction here at this point D, for example, we can call it D, and also we will have one moment. This we call it MD. You can calculate D. D is clearly equal to 400, and MD, of course, the direction must be in this direction, not this. It should be counterclockwise. MD is equal to 400 multiplied by its arm, which is this length, and it's equal to 4 centimeter here. This is the length of this arm multiplied by 4. So you can substitute, instead of this link DE, you can substitute this force and couple system, and now you can solve this beam to obtain the internal reactions. Okay, as I told you, you can substitute the 400 Newton load at E by replacing by a 400 Newton force and 1600 Newton per centimeter couple at D, and we can remove this R. Here you can see this is the resultant system. We have two reactions in the supports. We have one external force 400 Newton, which is substituted due to that arm, and also this couple 1600, and also we have one distributed load. Now, can you tell me how many sections do we need to obtain the internal shear force and bending moment for this beam? Yes, exactly. We need 3 sections, and the first section is for X between A and C here. The second section is for the X between C and D in this area. And finally, the last section is for the X between D and B. So we need 3 sections, and we can obtain the shear force and bending moment for all the beam by these 3 sections. The first section, as you can see, is for the X between 0 and 12 centimeter. Or X between A and C. We can write the force equation and moment equation. This is the free body diagram for this part. The length is X, so the equivalent concentrated force for this distributed load is 40 times by X, because this length is X, so the equivalent distributed concentrated force is 40 times by X, and the position of this force, the equivalent force, is X divided by 2, because it will be applied exactly at the center of this rectangle. Okay, so it will be 40X, and the distance of this force is X divided by 2. We will have one shear force and one bending moment, and also the external reaction, which is 550 Newton, and this is obtained from the external analysis. Now we can write the force equation. If you write the force equation in y direction, we will have the 550 Newton in upward direction. we have one force 40x, which is in downward direction, minus 40x. And also we have the shear force V, which is again negative because this is down in downward direction. So from this equation, we can obtain that V is equal to 515 minus 40x. Here you can see in this example, the shear force is not a constant value because here we have distributed load. So due to this distributed load, the shear force for this interval between 0 and 12 centimeter is a function of x. And for the moment, we can write again the bending moment, we can write the moment equation about this point, about the cut point. We will have a moment due to this 515 Newton force multiplied by its arm, which is x. We have a moment due to this 40x Newton force multiplied by its arm, which is x divided by 2. And finally, we have the moment m. If we assume that, for example, the counterclockwise direction is positive, m will be positive, and the moment due to this 40x Newton is positive, here you can see. And finally, the moment due to this force, 515 Newton, will be negative because it will be in clockwise direction. And finally, it must be equal to 0. And from this equation, we can obtain that m is equal to this term. As you see, because of this distributed load, because of this force, the shear force is a function of x, and the bending moment is a function of x squared and x. I mean, this is a polynomial from order 2 because we have a distributed load. So this is the first section, and now we need to obtain the free body diagram for the second section. Is it clear? Any question from this part? This x squared will be calculated here. Here we have 40x multiplied by half times by x. So 40 multiplied by half is 20. Yes, and here we have x multiplied by x is equal to x squared. So this term is 20 times by x squared, and here we have minus 515 times by x. When you move it to the other side of the equation, it will be minus 20x squared, and it will be plus 515x. Okay, any other question from this part? Okay, so this is the bending moment and shear force for this part. The next section is between C and D. In this interval, if you plot the free body diagram, the distributed load will be completely appear in this free body diagram. As you can see, this length is equal to 12 centimeter. And as you can see, the equivalent force is 480. It's not a function of x because this is appeared here completely. And the distance between this equivalent concentrated force and the section is x minus 6 because this length is 6 centimeter and the total length is x. So this distance is x minus 6, and we have 515 Newton, similar to the previous part. We have the shear force and bending moment. Now we can write the force equation in y direction. We will have the force equation in y direction. We will have 515 Newton minus 480 Newton, this force, and minus v, it must be equal to 0. And you can conclude that v is equal to 35 Newton. As you can see, the shear force again is a constant value because there is no distributed load in this area for x between C and D. The The bending moment can be calculated from the moment equation about this point. We will have one moment due to this force 515 multiplied by its arm, which is x, a moment due to this 480 multiplied by its arm, which is x minus 6, and finally the bending moment m. And if you simplify this, again you can obtain the bending moment as a function of x this time. Okay, so this is similar to the previous example. And finally the last cut, which is for the x between D and B. In this case, and in this section, when you plot the free body diagram, in addition to the distributed load and the external reaction, we will have the Newton and couple system of 400 Newton and 1600 Newton force, moment here. This time the distance between the cut and the 400 Newton force is x minus 18, because this length is 18, the total length is x. The distance between the 480 Newton force and the cut point is again x minus 6, because this length is 6 again. Of course, this x is different because in this interval, x located between D and B, and its numerical value is different. So again, you can write the force equation in y direction. If you write the force equation in y direction, we will have V, the shear force, with a negative sign, because this is in downward direction. We have minus 480, we have minus 400, and we have plus 515. If you simplify this equation, you can obtain that V, or the shear force in this interval, is minus 365 Newton. And again, if you write the moment equation about this point, we will have a moment due to this force 550 Newton. We assume that the counterclockwise direction is positive. So we will have a moment due to this force 550 Newton, which is positive, multiplied by its arm, which is x. We have a, of course, sorry, about the direction here, we assume that counterclockwise is positive. So the moment due to this force is negative because it's in clockwise direction. We have another moment due to this force 480 Newton multiplied by its arm, which is x minus 6, and its direction is counterclockwise. So this one is positive, 480 this term multiplied by x minus 6. We have a moment 1600 Newton centimeter, which is in clockwise direction. So it will be negative. Here you can see we have a negative sign, 1600. We have a moment due to this force 400 Newton multiplied by its arm, which is x minus 18. So 400 multiplied by x minus 18, and the direction will be in counterclockwise direction, so it will be positive. And the last one, which is the bending moment at the cut point, and this is in counterclockwise, and it will be positive. From this equation, you can obtain m as a function of x. As you can see here, m is a function of x, and this time you can substitute x and obtain the value for the moment, bending moment, in this area for the point between D and B. Okay, any question from this example? Okay, so we can plot the shear force and bending moment diagram. As you can see, the shear force for versus x, we have 3 cuts and 3 different equations for the shear force and bending moment. The first one is a linear equation of x. As you can see, start from 515 and at this point it's equal to 35 Newton. You can check it again. I should mention that you can check your values from both sides to check your results, the accuracy of your result. Again, in this interval, the shear force is constant between point C and point D. And after that, for the interval between D and B, when X is between 18, here at this point X is 18 and at this point is 32. So for the X between 18 and 32, the shear force again is a constant value and it's equal to minus 365. But the bending moment in the first interval when X is between 0 and 12 is a function from order 2, a polynomial of order 2 as a function of X. And again, start from 0 at this point. And here it's equal to 3,300. And again, it will be a linear function of X for the interval between C and D, or when X is between 12 and 18. And finally, for the last one, we will have a linear function of X for the bending moment for the interval X between 18 and 32. Okay, so this is the bending moment and shear force diagrams versus X. Just to mention that to check your results, in the bending moment diagram, you can see this is a continuous line, except this point when we have a concentrated moment. Here you can see, let me change the color. At this point, you can see that the diagram is not continuous because here we have a concentrated moment, this 1,600 Newton. So you should check your bending moment must be continuous except these points when we have a concentrated moment and we will have a jump. And here this jump is equal to 1,600 Newton meter. I mean, if you find the difference between 5,110 and 3,510, you can see that we will have a 1,600 jump. And also we have the same scenario for the shear force diagram. I mean, the shear force diagram must be continuous except these points that we have a concentrated transverse force. Here we have a 400 Newton force, so we have a jump of 400. You can see the difference between this force 35 Newton and minus 365 Newton is a jump of 400 Newton, and this is due to this concentrated force. So again, you can check this point to check your results by using this point and check that your result is correct or not. Okay, because this is a personal Zoom meeting link, I have a time restriction of 40 minutes. So I should wrap up this session at this moment because my time is almost finished and only I have 1 minute. If you have any question, please ask. Otherwise, I will wrap up this session. Okay, thank you, and have a great weekend and holidays and happy Diwali, and thank you for your attention again. Thank you all and bye.
Thank you.